a conjecture is it's very encouraging now, and saying is that if Mn Gij F is a complete, so here it's different from the remaining geometry. When we say complete, it actually implies non-compact. So here we means either compact or complete non-compact. Is a complete shrinking gradient Ricci soliton with Ricci positive. Then Mn is compact. So, well, there's a little bit gambling there, but I'm willing to bet $500 US dollars. That's a generous one compared to the some of the number theory ones, right? only $100. So yeah. So this, of course, if that's true, then that will be very nice. So now let me say a few words about it. Before, there's one reason is the examples. And of course, now this is even a stronger supporting. So can we go a step further? But one of the original motivation, even I asked before, so this one actually was mentioned after Perriman's result, mentioned in my 2009 that survey paper, and that was one of the problems there. And yeah, so let me say a few words. And I think that Ovidio is going to present the proof, right? I can say a few. I can give a very brief sketch, and details can be referred to his lectures. Oh, maybe I erased some of the things could be useful. Anyway, so let me say at least two reasons, right? So, one of them is, what about examples? So the facts is so far there's no example of a non-compact shrinking gradient Ricci soliton with Ricci curvature positive everywhere, even the rotational symmetric ones. Right? So one of the what are the examples? So for example, the so n equal to 4. So for example, the so-called FIK soliton, shrinking soliton. Does not have So let me say a few words about this the soliton. So maybe I just say n equal to 4 because low high dimension, but that's also for example, in n equal to 4, so this is the Feldman, Tom Yeomanen, and Knopf. So construct the only example non-example non-compact, only non-compact example. in dimension 4. So this one, if we have anyone in algebra geometry, this is called O-1. That's talk about line bundle over CP1. So that's the total space. The total space is M4. Or you can say M4 is equal to the C2, and this is blown up at the origin. That's the same thing. So complex blow up at the origin. So essentially, as you take the origin, you replace by S2 or CP1, and that becomes non-compact. That would be related to the example of that Koizhou construct. So actually, this is a U2 invariant example. But Ricci is not Ricci has very changing signs. And the high dimensional, you have also UN invariant ones. So the complex rotational symmetric ones does not have the Ricci positive. And I think that's a strong sign in some of the strong indications. So if the most symmetric ones has the largest symmetry, doesn't have the positivity. So this is very much different from the steady and expanding solitons. Okay, so this can be constructed by ODEs, nonlinear ODEs. So I'm not going to describe the details. So this is a strong supporting reason. And of course, here is also secondly is based on the arguments that Ovidio and Japin presented, is saying that we have to be, what do we say? 更加大胆一些，更加想象的should be explore more of the structure equations and potential functions, and that's what encouraged. So maybe in remaining a few minutes, maybe I just use 5 minutes to sketch their arguments. And hopefully we have some talented even PhD students or grad students can be more creative in finding some new ways to prove things. Okay, so that, yeah. So let me sketch a few and of course in the years between 2008 or 9 and 15 we have had a few general understanding of non-compact manifolds of the shrinking solitons. So sketch of the proof by Japin and the results, their theorems. All right, so we need, first of all, step 1 is explore, of course, the curvature explores the how the Ricci curvature evolves, and that's the twice. In this case, is just the Ricci minus Riemann times Ricci, or maybe maybe higher right on intensus Rij equal to Rij minus twice, which I erased a minute ago. And the only place they use the non-activity is that, and the sectional curvature non-active. In the sense that if sectional curvature is non-active, then this implies the Riemann times Ricci is going to be non-active. and you can throw it away. So essentially, this says the I'm going to throw in that one, right? Well, in some sense. But of course, this is a tensor. So in particular, the least eigenvalue, so lambda 1 equal to the minimum of Ricci satisfies lambda. Yeah, satisfies the in the sense of barrier. Because this is a Lipschitz function, and you can, in the barrier sense, that satisfy this equation. So this is positive, right? Okay, so that's a crucial look at the eigenvalues of Ricci. Now, so step 2 is combining and the fact the potential function satisfies n over 2 minus f, basically like the eigenfunctions. And apply maximum principle, so maximum principle argument, which is also previously explored by Ben Chao, Pen Lu, and Boyan, is showing that the lambda, so actually this is true for any functions u. So this can be any functions of u less than or equal to u, and u positive, can be bounded from below by the potential functions. Right? So this is an elegant argument, a fact that you can do so by Ben Chao, similar to the argument. But now is step 3 is what they, but so in the sense that now this is going to be equal to c and distance, the quadrate over the distance squared by using myself and the Tanzhou potential function. So the potential function in the sense that what we prove is any non-compact M3GIJF shrinker has potential function fx is basically 1/4 of the distance squared above and below outside the compact set. So in the sense, potential function is like exactly like on the Euclidean space, the distance functions. So that particularly, step 3 is that actually combine this is you using the gradient R, right? So now using gradient R is twice of Ricci of grad f, and the Ricci is bigger than or equal to c over f now. This implies the scalar curvature has to be log gross. Yeah. So another constant times log of distance function outside. But that's going to be a contradiction to a fact that we also early on observed in the sense that average scalar curvature. So here it says the Ricci curvature can decay at most quadratically, and that forces the scalar curvature to pointwise grow logarithmically. And this implies, but on the other hand, this is a contradiction. So I'm not going into any details, and then this is a contradiction. To the fact we proved earlier on is that for any x naught, a distance r, the scalar curvature is bounded by n over 2. Of course, there's some also volume estimates and other things. So in the sense that if, by contradiction here, if M and G F is non-compact. So all case, because only when it's non-compact, we know how the potential function behaves at the infinity. If it's compact, we can say almost nothing. And that is going to be the next lecture. We're going to discuss the compact case, and at least in 4 dimensions. So I'll probably stop here. So,
in question of, so
yeah.
What do you do if that
F
f equals to 0?
equal to 0. I mean, in the, well, if you set F equal to 0, that will be Einstein, and that's compact already. So in the sense, if you have the shrinking soliton, if F is equal to 0, then you would have the Ricci is, say, for example, like so Einstein constant is positive, and of course we know that's must be compact already. Yeah. Oh, yeah, certainly that is also an issue. That can be another thing is, right, what about its non-gradient? There are some of the equations that works, but some of the, for example, like, then we don't know how there's no potential function, and might be, that's still an interesting question. Some of the techniques clearly fails, and one might needs to do some, you know. Yeah, in the sense, the only thing we know is if it's if the non-gradient one, well, sort of only vector field. If the curvature is bounded, then we know it must be gradient, right? But if curvature is not bounded, we actually don't know. Do we have any? We don't even have any examples. But that's certainly an interesting part is what can be, done if it's just a vector field. We still have some equations, but not to the potential function level. Yeah, that would be an interesting question, yes, to explore. So I'll let Japin think about more, or other think about more. Yes. But I think that will be, yeah. So we like to see how essential is the sectional curvature ones here. Yeah. So sectional curvature. Is there any way there's an average sense argument? Well, they must have thought about it, but that's not so clear, right? So in the sense, to get to the contradiction is we don't only need to average something. Well, that last step is only in the averages and contradiction, but they prove much more. It's point-wise must grow. So naive sort of thing is, can we do an average, work on the average, and then the Ricci curvature hopefully will be enough. Okay, so I think, yeah. Yeah, so this will be optimal, of course, if that's the case, yeah. of course, one of the other non-compact case is also the recent results of Brad Kochua and combine Brad Kochua and Luan and Japing and Orvelius results. So I think you're going to hear more. So actually, we have more hope for non-compact ones. That's the thing. So what about compact ones? So I'm going to probably state maybe two or three open problems, but depends time, maybe I hopefully can state two problems. So for 4 dimensions, we're going to concentrate on 4 dimensions, compact. Actually, we don't really know much. So now, next we're going to do the compact. Shrinking gradient Ricci solitons. Some of the things you can extend to non-gradient ones. So here we have Mn, Eij, and F, say, is a compact shrinking. So gradient Ricci soliton. Well, what kind of results we have? Actually, not much. For example, then we know chi 1 of Mn is finite. So this is a result by William Wiley. Compact case was due to two Spanish mathematicians. Sorry. Right, so this is actually the Wiley. Yeah, so these, let's see. Even when Mn is non-compact. Okay, so this is the when it's compact, that's a special case by two Spanish mathematicians. So this resembles like the Myers theorem, right? Remind us like Myers theorem, where Ricci curvature has a positive lower bound and it's compact, and then the fundamental group finite. Oh, what else? What else do we know? Yeah, diameter is lower bound, right? But for geometry, so for example, I would say ask, what about B? So this implies, of course, the Betti number B1 is equal to 0, right? So question is B2? Can we say anything about B2? Second Betti number, especially if it's 4 dimension. Well, we don't have anything, right? Well, in general, right? So suppose we have a compact shrinking Ricci soliton. Can we say anything about B2? For example, that B2 has to be always positive. Is there any reason? Right. But this is actually it's not known at all, so completely open. What I'm going to want to say so here I want to ask is, now here is an open problem. Does the Hitchin, so we're going to so-called Hitchin-Sump inequality hold for compact 4D shrinker, Ricci shrinker. So let me explain what is the Hitchin Table. And this is inspired by the Einstein case, four-dimensional Einstein case. So see what the Hitchin Table says. So Hitchin Table. So here's the case. So now for any compact M4 and metric remaining manifold M4 Gij, because the four dimension, we know we have the two forms splits into the 2 plus and the self-dual and anti-self-dual forms, right? We all know that. So here we have a Hodge star operator, which on the two forms to two forms. And so the four dimension particularly, so star is equal to identity. So this one here is the, as we know, is the star is self-dual ones, eigenvalue equal to. So here is, so this is so-called self-dual two forms, means and for any two form is equal to self, and this one is anti-self-dual. Star of eta is equal to minus of eta. So for eta is in. Okay. All right. So this is the a very important structure to study four-dimensional remaining manifold, right? That's well known. So now, let's say, so here we have a definition. M4 Gij is called self-dual if the Weyl curvature, if the Weyl tensor has W minus identically equal to 0. So here will be anti-self-dual if that's the W plus will be equal to identically 0. So now here, in general, W is equal to W plus, right? So here the Weyl is like a full curvature tensor which acts as a quadratic form on two forms. So Weyl is the two form to two form again, okay? Because the first two is like the curvature operator. First two is skew symmetric. Third and fourth is skew symmetric. You can switch. So that's a bilinear form. In this case, I actually have that decomposition. So it depends on. All right. So now, what's Hitchin Table? So the four-dimensional now the Gauss-Bonnet. Gauss-Bonnet says the following: the Euler number of M4 can be written as an integral. It's A1 over, so use the in terms of curvatures, 1 over 8 pi square. An integral here will be by curvature decompositions. You have the following three parts using the curvature decomposition. So the first part is the Weyl part, which now orthogonal splits in these two parts. So this essentially is equal to Weyl norm squared, Weyl tensor. Okay. Then you got the traceless Ricci part, and then you have the scalar curvature part. Integrals. right? So here the volume dimension 4, 4D. So that's why so here Ricci is just the trace part, which is n over 4. So 1 over 4 scalar curvature times. Yeah. Now another one is so-called Hertzsprung signature formula. I'll write it down and I'll explain it. So here is the another standard is tau of M4. Is also, this is 1/3 of so-called Pontryagin number, and you can use that. That will give us 12, 1 over 12 pi squared. And integral is W plus square minus W minus squared. And this is equal to so I have to say a few words, going to be equal to B2, B2 plus minus B2 minus of M. So now what is so here you have what is the intersection form, and B2 plus B2 minus is equal to second value of B2. All right, so you have the H2 of M4 and Z, and you have the pairing intersection form going to Z. So you got 2-dimensional thing, 2-dimensional transverse intersections. You can counting the intersection with multiplicity, and then you got you're going to this one. So this is a bilinear form. In bilinear form, you can diagonalize. You got the positive eigenvalues and minus the number negative eigenvalues, and that's the signature. Okay. So the dimension is equal to B2, right? Yeah. And so it gets split. So that if you combine these, so combine the two. Of course, the early observation is combine. So 1 and 2, you combine, you clearly got one quantity is twice to make them 2 chi plus 3 or minus tau is going to be equal to essentially you got 4 if you W plus or minus depends on the plus minus squared minus let me just get the constant right. You can do the arithmetics, minus trace norm squared, and then plus scalar curvature squared over 12, and d mu g. And here, as we move it, that would be giving us 1 over 8 pi squared. Okay. So if you know that, and Thumb actually was in 60s, so the clearly. So now, if M for G is Einstein, then and that is the Hitchin Table inequality. Or often written as 2, 3 absolute value of tau. Yeah. So it's between the Euler number and signature. And this is the only known topological obstructions for Einstein manifolds in positive Einstein constant case. So this, and of course Hitchin went on to say more what happens when equality holds, etc. So this is just part of the so-called Hitchin when you have inequalities. So a natural question is, our Ricci solitons is some extension, natural extension of Einstein matrix. And we also like to see if there are any topological obstructions. So the question is, does the same inequality hold for compact Ricci solitons? And of course, only meaningful one is the shrinking, because if it's static and expanding compact, then they have to be Einstein already. So only the remaining questions is the shrinking ones, four-dimensional. All right. Well, so you can, of course, now so this term is the only non-positive term that we have to handle. And of course, we have the equation. So you can do some calculations. So for example, I'll leave as exercise that you can change you can modify this thing a little bit by using the soliton equation, at least to the following ones. So that's not so difficult. And so this is, I think I start wonder about this is probably 2004, 2005, like when we started to consider Ricci solitons a little bit more. That's just a natural one if you know the Einstein case. And this appeared like at least in 2006, my earlier, more preliminary survey articles. So here is a lemma. So a remark maybe is when M4 CIJF is a compact shrinking gradient Ricci soliton, then we have the following lemma. We can just transfer the L2 norm of the Ricci, trace of Ricci, into the 1/4. And this is the, let me see, do I have the right constant? Actually, I've got this. Basically a scalar curvature, and then minus the volume of M, something like that. I hope that I did just checked a little bit. Well, this is a calculation. Whether I got the constant right for. Yeah. So basically, then the corollary. This is, in the sense, is now the 2 chi plus or minus 3 tau is going to be equal to 1/48 pi squared and 24 of W plus minus squared minus scalar curvature and plus 6. Yeah. And that is the one. So it's all about the relations of scalar curvatures and etc. Another comment is if you know it's scalar, then the point-wise these two are the same. But of course, four-dimension scalar, we already know that they are classified. But at least, so the question is how these quantities, so it's about the via curvature part and how the scalar curvature, etc., they can react. So far, still, I think, as far as I know, that's still open. I see. I'm willing to give like a $50. That means you may have to spend more time on it. Because this is a pure, this I actually, it's like, ask whether Einstein extends. I think the other one, without the example, even in most rotational symmetric one, unless we construct a remaining one, then that could be different. But I think the other one I'm had more confidence because the example here we only, of course we have examples, but those are tailored and very special, brought up 1 and 2 points. We know the Euler number and the tau explicitly, and actually if you use general theory, then this one is actually identically 0. So I don't know. I have less confidence because for the compact ones, we know much less. Yeah. Well, don't be discouraged. We are not working for money, right? So that's still very interesting. This will be the first obstruction for compact shrinking solitons. So that would be, from that sense, that would be very interesting. So I think I just say this much because it's all here. You have to play with it. But so far, I know a few people tried, including myself very early on. I haven't tried. I think the thing is have to involve the wire part a whole lot more. So you try to maybe study W plus and these things. But so that's the should be a new interesting part. If it's Einstein, there's more other things. Okay, so I'll just say this much. All right. So actually, our graduate students, if you know a little bit for manifolds of these things, you can start to play with it. Right? Yeah. The other one, which will need more interesting, in the sense needs much more mathematics from different aspects. So I'm going to mention the second one, and these are tied to the complex. A bit complex and complex structure and Hermitian structures. But again, I'm going to focus on the 4-dimensional. So hopefully, is 4-dimension, we can do more. And of course, Ricci flow, as far as Ricci flow is concerned now, 4-dimension would be most interesting part in the remaining case. And then, of course, we have the Cayley in more general dimensions. So I'll state it, and then again, we have about 10 minutes, and maybe I'll let Sutton go, and we will extend for another 5 minutes, right? I have 3:20, right? Okay, so here's the second one. This is motivated by Lebrun's work in the following sense. Is here I will probably just say question here. So let M4J be a complex surface. Real 4-dimension, complex 2-dimension. And let G be a non-Einstein shrinking Ricci gradient Ricci soliton. Well, of course you got pair metric. All right. Which is a Hermitian. With respect to the given complex structure. So here I'm less confident, so I ask the question, is it true that M4JG is a Taylor-Ricci soliton? shrinking, of course, right? So it's more about uniqueness or rigidity in the with respect complex structure, Hermitian structure, and what. That means that is basically equal to either Mai and Koizo on CP2 blow up CP2 bar, or this is Shuja 1 and Xiaohua Zhu, 1 Zhu soliton on CP2 blow up 2 points. These are the only four-dimensional compact shrinking solitons we know, right? Now, what's the motivation or background? Well, essentially, the motivation comes from LeBron's work. If the G is remaining Einstein, but Hermitian with respect to J, and he has. So let me state his result. And this is a more challenging problem, I think, but would be interesting to see how the complex structure and the shrinking Ricci soliton equation interplays. Now this is the motivation is LeBron's work on Einstein for the Einstein case. For the Einstein case. And this is appeared in JDT, and I believe is 2012. So here we basically is replace. So he says is the following. So suppose M for G is Einstein, and suppose M for G is complex surface. G is Einstein, and Hermitian. So it's basically just replace the soliton and Hermitian with respect the following three situations. One is M There's two exceptional cases. G is the Page metric, Page Einstein metric, up to scaling, okay? On CP2, blow up CP2 bar. So in this case, this is remaining, but knows it's the Hermitian, okay? So this is not Kähler Einstein, but it's Einstein, and actually what we call something called a locally conformally Kähler. And this is tied to the Calabi structure matrix, actually called locally conformal Kähler, say. Or, so we have two cases, right? Like, or the other one, so essentially is only two exceptions. G is the LeBron, chain, LeBron, Webb, Einstein metric. Again, you can, of course, always scaling a constant on CP2, blow up 2 points. So this is the work, so that their work is more recent. This is probably 2009 or 2008, JAMS, Journal of AMS. And the page metric was probably 1978 in gravitation or so in physics. And this is so-called by taking the Hawking type examples in Lorentzian case and doing so-called Wick rotations, you construct one. Yeah. So this says if it's a Hermitian with respect to some complex structure, in the sense is that except these two cases, they have to be already Kähler-Einstein. So we ask actually if these are the only two non-examples, but if it's Hermitian, do they have to be already Kähler-Einstein? That's more like explore the complex structures. In the sense that at least the current proof of LeBron involves Einstein metric in a rather essential way. So will be interesting to see if that kind of thing will be true, or at least say something about it. Yeah. And I think that's the time that Susan has to go. Okay. All right? Yeah, so this will be related to the case. So in a sense, Einstein in LeBron's result plays an essential role in several. One part is that Hitchin-Thorne needs to be explored, use the Hitchin-Thorne encoding in a very heavy way. Of course, if we can bypass Einstein, get Hitchin-Thorne, that's already, for example, if we know Hitchin-Thorne it holds, then I can prove that at least a diffeomorphic to, so M4 has to be diffeomorphic to CP2 blow up a few points, up to 8 points. That actually can be proved, just knowing the Hitchin-Thorne. But you need to know, to say other things, you need to know more. So that's why Hitchin-Thorne is also a useful part to know in this case. Any questions? Yeah.
At the moment, when T is 1 over 2 rho, do you require any condition on metric taken together for diffeomorphism taken together nicely?
Say it again. You say.
So when T is equal to 1 over 2 rho.
Oh, T is equal to 1 over 2 rho. Oh. Yeah, because actually that's a singular time, for example. That essentially the curvature blow up. So you do not have, the solution exists for minus 2, well, if rho is positive, right? So, yeah. So, wait a second. You get the 1 minus 2 rho T, right? So you are talking about the one that's equal to 0.
So there's no condition.
Oh, actually, that's a blow-up time. So the metric will be, it's no longer, you're sort of like you do not exist at that point. It's only before, right? If it's shrinking ones. Yeah. But not so much, right? But before that, it's just a sort of homothetically, except you do a little bit reparametrization. And of course, we don't, so in a sense, in low dimensions, you only have the spheres and other things. You don't really have non-trivial examples. Only start when dimension equal to 4 or more. Dimension 4 is the first dimension that we have these two examples, compact. And then the dimension is increased. You get more examples by more general conjugate by Denser and 1 and others like Mutao and Futaki. have more examples. But up to 4 dimension, FIK example is the only non-compact, and these two are the only compact ones. Yeah.
Right. Your formula, 1 minus 2 over t is in the numerator.
In the numerator. Right. That's right. So it's gradient of f over 1 minus 2 rho t. Yeah. So you exist up to that time. Yeah. Well, if you evolve under the Ricci flow, that's the time sort of curvature blows up, in some sense. Yeah. And you exist up to before that point, before that time. If you just think about sphere, then you shrink to a point already. Yeah. Okay. Well, yeah. So, if I can say a few words about what's the LeBron, but yeah, if you're interested. But yeah, I think. Yeah, tomorrow. Tomorrow I'll be say. The other one is that probably in theory is the stable ones. So maybe I'll start tomorrow. So tomorrow morning I mentioned again some of the use of second variations. In the mean curvature flow case, there's more results known, and then I move on maybe to some of the steady solitons. There's some question on steady solitons, which is of a different nature. Because that's more like Ricci flat cases. So I'll talk about a bit both remaining and the Kähler steady Ricci solitons. Okay. Oops. So we was I guess we'll resume tomorrow.